Last year, something drifted into our solar system that was never part of it. It condensed around a star that isn't our sun, somewhere else in the galaxy, possibly long before our own sun even existed. James Webb didn't just photograph this visitor, it broke the object down chemically. For the first time, humanity obtained a direct chemical readout of material from a planetary system beyond our own. We didn't have to send a spacecraft across the stars to collect it. The object came to us. And what Webb and other observatories found inside this comet is so different from anything we've cataloged in our own solar system that researchers are reconsidering what they thought they knew about how planets and comets form. The story began on July 1st, 2025, when a telescope in Chile detected a faint point of light moving across the sky. The telescope belonged to the ATLAS network, the Asteroid Terrestrial Impact Blast Alert System, a NASA-backed program designed to discover objects that could potentially threaten Earth. But this object wasn't coming toward us as a threat. Its trajectory was hyperbolic, moving too fast and along a path too open to have originated inside our solar system. It was traveling through our neighborhood, but it had been born somewhere else. Scientists designated it 3I Atlas, with 3I marking it as only the third confirmed interstellar object ever observed. The first was Oumuamua in 2017, an elongated and mysterious object that never produced a detectable coma and remains debated. The second was Borisov in 2019, a genuine interstellar comet, but one that was too faint for the kind of detailed chemical study scientists wanted. Then 3I Atlas arrived, and this time astronomers had something different. Advance warning, and enough brightness to prepare. Hubble, James Webb, ALMA, the Very Large Telescope, Mars orbiters, SWIFT, SphereX, TESS, and other instruments turned toward it. When it was first detected, it was already traveling at roughly 137,000 miles per hour inside Jupiter's orbit and heading toward the Sun. Hubble later estimated its solid nucleus at somewhere between roughly 1 or 4 and 5, 6 kilometers across, while images already showed a coma and the beginnings of a tail. 3I Atlas reached perihelion, its closest point to the Sun, on October 30th, 2025, at about 1.36 astronomical units. That meant it never approached the Sun as closely as Earth does and posed no danger to our planet. Yet the distance was close enough to activate the frozen material on its surface and inside its nucleus. The reason this object mattered so much was that the previous 2 interstellar visitors had given astronomers only limited opportunities. Oumuamua vanished before detailed chemical observations could be organized, while Borisov was too dim for the deepest spectroscopy. 3I, Atlas, by contrast, brightened dramatically, reaching around magnitude 9 near perihelion, and giving researchers months to coordinate observations. The first major discovery involved water. NASA's SWIFT observatory observed the comet in July and August 2025 while it was still approaching the Sun. SWIFT detected ultraviolet emission from hydroxyl, a molecule produced when sunlight breaks water molecules apart. Solar system comets generally contain roughly 1 heavy water molecule for every 10,000 ordinary water molecules. But 3I Atlas produced a ratio more than 30 times higher than the typical value measured in our comets, and more than 40 times higher than the ratio found in Earth's oceans. This wasn't a small difference. It was an extreme chemical signature unlike anything previously measured in a comet from any planetary system. Salazar Manzano explained that the unusually high deuterium level suggested that the cloud of gas and dust from which the comet's parent star and planets formed was much colder and chemically different from the environment that produced our own solar system. That result transformed the comet from an unusual visitor into a kind of natural time capsule. The deuterium to hydrogen ratio preserves information about the conditions present when the material formed, meaning scientists were effectively reading a chemical record from another planetary system without ever traveling there. Every comet carries clues about its birthplace, but 3I Atlas carried clues from a birthplace humanity had never sampled before. The next major discovery would reveal another layer of that story, this time involving a molecule that is particularly sensitive to temperature: methane. James Webb observed 3I Atlas multiple times, but the key chemistry observation came in December 2025, roughly 2 months after perihelion, when the comet was heading back out of the solar system. Webb used its MIRI instrument in spectrometer mode, allowing researchers to determine not only which gases surrounded the nucleus, but also where those gases were concentrated. The observations revealed water vapor, carbon dioxide, and methane. The methane detection was particularly significant because it represented the first direct detection of methane on an interstellar object. Methane becomes gaseous at extremely low temperatures, and in our solar system it is generally associated with comets that either contain significant quantities of it or become warm enough for it to escape. The fact that Webb detected methane after perihelion suggested that the molecule had been buried beneath the comet's outer layers. Before the sun's heat reached deep enough, that material remained sealed. As the comet moved through its closest solar approach and then began departing, heat gradually penetrated the outer crust and opened access to material that had remained protected for an enormous period of time. That gave scientists a glimpse beneath the comet's radiation-weathered exterior. During its long journey through interstellar space, the surface would have been exposed to cosmic radiation and other energetic particles, gradually altering the chemistry of the outermost material. Beneath that layer, however, the interior could remain much closer to its original state. Webb's observations showed that water was distributed broadly throughout the coma, with much of it apparently coming from icy grains drifting away from the nucleus. Carbon dioxide and methane, by contrast, remained more concentrated around the nucleus itself, consistent with these gases being released directly from solid material near the surface. The methane-to-water ratio was also unusually high compared with solar system comets, while the carbon dioxide abundance pointed toward a formation environment that differed significantly from the one that produced most known comets here. As the object moved farther from the sun, water production declined faster because water requires more heat to vaporize, while methane and carbon dioxide continued to linger somewhat longer. That sequence matched the expected behavior of a comet with this unusual composition. But Webb's chemical picture was only one part of the story. Another observatory was examining the atoms themselves, looking at isotopes of carbon and nitrogen for clues about the comet's deeper history. The European Southern Observatory's Very Large Telescope followed 3I Atlas through late 2025 and into 2026. A team led by University of Edinburgh astronomer Cyrielle Opatom used the UVES instrument to examine isotopic ratios in cyanide molecules inside the comet's gas cloud. Carbon exists in different isotopic forms, including carbon-12 and carbon-13, while nitrogen occurs in forms such as nitrogen-14 and nitrogen-15. The relative abundance of these isotopes can preserve information about the temperature, radiation environment, and chemical conditions that existed when the material formed. The measurements from 3I Atlas again fell outside the normal range seen in our own comets. Researchers measured a carbon ratio near 147 and a nitrogen ratio near 343. Solar system comets generally show a carbon ratio around 90 and nitrogen ratios roughly between 130 and 170. The interstellar comets' values, therefore, weren't simply unusual versions of familiar solar system chemistry. They pointed toward a fundamentally different environment. The results, published in Nature Astronomy in July 2026, were consistent with formation in a cold, metal-poor environment, potentially associated with an earlier stage of the Milky Way's history. Put all those measurements together and the picture becomes increasingly striking. The extreme deuterium signature suggests very cold formation conditions. The methane buried beneath an altered outer crust indicates material that remained protected for an extraordinarily long time. The carbon and nitrogen isotope ratios point toward an environment chemically different from the one that produced our solar system. One possible interpretation is that 3I Atlas formed in the outer region of a protoplanetary disk around a star considerably older than our Sun in a colder and less chemically enriched part of the galaxy. At some point, the comet was thrown out of its original planetary system. A gravitational interaction with a planet, a close stellar encounter, or another process could have provided enough energy to eject it into interstellar space. Once free, it may have traveled for billions of years, carrying its frozen chemistry through the galaxy. During that time, radiation could have transformed its outer layers while leaving deeper material relatively untouched. Then, in 2285, pure chance brought it close enough to our Sun for the frozen material to become active, and close enough to Earth for humanity's telescopes to read the resulting gases. James Webb was central to that opportunity. NASA Goddard scientist Martin Cordner had been preparing for the possibility of another interstellar visitor since Oumuamua appeared in 2017. The goal was to have a plan ready so that Webb could respond rapidly whenever another object was discovered. When 3I Atlas appeared in July 2025, that preparation became useful. Webb was able to capture a detailed mid-infrared chemical record while the comet was still active. The resulting dataset became one of the most chemically detailed records ever assembled for material originating outside our solar system. The broader implication is difficult to overstate. Scientists have studied hundreds of comets from our own system and naturally use those objects to build models of comet formation. Until recently, however, there was no way to know whether our comets represented a universal pattern or simply one local variation. 3I und Atlas provided the first strong evidence that planetary chemistry can vary dramatically from one stellar system to another. Its measurements don't merely add another comet to a catalog. They expand the range of environments that scientists must consider when modeling how planets, moons, asteroids, and comets are created across the galaxy.